Welcome to our first advanced Artec Studio training webinar. Now let's jump into our first topic, lock-in frames and lock-in objects. Today we're discussing what I consider to be some of the most unnoticeable yet vital tools in Artec Studio, lock frames and lock object. Unfortunately, these two are frequently confused because they both involve the word lock, but they operate on completely different levels of your data. To ensure we're all on the same page, we're going to start by looking closely at where they are located and exactly how their purposes differ. As you can see on the slide, both options are tucked away in the right-click context menu within your workspace. Lock frames is internal. It locks the individual frames within a single scan relative to each other. This is specifically for handheld data, like from your EVA, Leo, or Artec Spider 2, where you want to ensure the internal registration of a scan doesn't change during a global registration, even if you move the scan as a whole. Lock object, on the other hand, is external. It locks the entire scan or model relative to the coordinate system. Once this is on, that object is an anchor exactly where this buttons live in the interface, so you can find them instantly in your own projects. So let's look at this in practice using the project captured with Spider 2. On the right side of the screen, you'll see our workspace populated with several high-resolution scans. When I right-click on any individual scan, the drop-down menu appears, giving us immediate access to the both lock comments. However, for those of you dealing with large-scale projects of multiple scans, there is a much faster way to manage this, so you can actually pin the columns for those settings directly to your workspace header. Like this. By doing this, you don't have to right-click every time. You gain a dedicated lock icon next to every scan name. And this allows you to assign or cancel any of the lock settings for a single scan, a specific group, if you need this, or even the entire project with just a single click. It's a small UI tweak that significantly speeds up your workflow where you're managing complex registrations. Okay, with that introduction out of the way, let's get into the specifics. The first feature we're going to master today is lock frames. The next portion of this webinar will be dedicated entirely to this tool. We'll explore exactly how it stabilizes your data during registration and look at the specific scenarios like complex handheld scanning with the Spider 2 or Leo, where pinning your internal geometry becomes the key to a perfect final mesh. Now let's look at how lock frames actually behaves. You can identify the status of your workspace by the icon that looks like a smaller fragment of a chain. When this is active, the internal registration of that scan is essentially frozen. So during global registration, the algorithm is prevented from recalculating the position of individual frames within that specific scan. However, this doesn't mean the scan is stuck in space. If you have multiple locked scans, Artec Studio can still move them closer together as units to improve the overall fit, all while keeping their internal frame data exactly as it was. Crucially, these locked scans still serve as a fixed reference. This allows you to reliably register your regular and locked scans against these anchors, ensuring that your most accurate data dictates the quality of the final result. So when exactly should you reach for this tool? There are three main scenarios where lock-in frames becomes essential for a high-quality result. First, we use it for registering, specifically when you're adding new scans to a scene that you have already perfectly registered. Second, it is a lifesaver for re-registering problematic or feature-poor scans that tend to break or drift during standard processing. And third, it is used for preserving accuracy in critical scans that must remain untouched to serve as a reliable geometric anchor. We are going to walk through each of these use cases one by one to see how they work. Let's look at this in practical application, adding data to a project where you already worked on. Imagine you are finished scanning this backpack and only notice a flow like an unscanned void under the strap after looking at the fusion. In a typical workflow, you just scan that missing part and add it to the project. However, to do this successfully, the object's overall shape must remain exactly the same as it was during the first session, of course. This is where log frames becomes a precision tool. Instead of running a fresh global registration and letting all your frames shift again, you log the frames in the original scans that you've already meticulously registered. This freezes your established work, allowing the new data to align itself perfectly into the gap without risking any drift or misalignment in the areas you've already perfected. Beyond just maintaining the integrity of your data, there is a massive speed profit to using this method. In this backpack example, the original project had 3,800 frames. Adding a small patch added only 400 more. If you run a standard global registration on every scene, this software has to recalculate the position of all 4,200 frames, which took about 62 seconds here. However, by using log frames on the original set, the algorithm only has to calculate the 400 new frames against the locked anchor. This dropped the processing time to just 13 seconds. When you're working with a massive dataset, this time savings really add up. Now let's move over to Artec Studio to see this in action. With a different type of object, this industrial part scanned with the Spider 2. Looking at the initial fusion or our first two scans, you can see a significant unscanned area indicated by the black void in the mesh. This is exactly the same situation as with the backpack that we've seen previously. We have already captured the third scan here, Spider 2.4, to fill this gap. So instead of reprocessing the entire project from scratch, I'm going to select Spider 2.2 and Spider 2.3 together in the workspace and activate these log frames. Remember, look for that icon that looks like a fragment of a chain. So now when we go to global registration, for all three scans together, the software will only focus on the fitting the new data to our logged base. It's worth noting that for a small object like this engine part, a time reduction of 10 or 15 seconds might not seem like much in the moment. However, the value of log frames scales exponentially when you move from the small components to large-scale projects like a full vehicle or complex industrial machinery. Those seconds turn into minutes, and those minutes turn into hours of saved processing time. To respect your time today and keep our webinar moving, we won't be running every single example live within the Artec Studio interface. We want to focus on the logic of the tools without making you sit through loading bars. Instead, we'll use clear and pre-processed examples for the rest of our scenarios so we can cover more ground together. And here you can see the results after the process was finished. Okay. Now we go into our second use case that involves those trouble scans we've all encountered, surfaces that are geometrically repetitive or feature poor, like a long brick wall or a flawed doorway. Sometimes when you run global registration on a large project, these specific areas can drift or lose their alignment because the algorithm is trying to find a mathematical fit across the entire scene. By using log frames on the scans that you've already manually verified as correct, so in our example, they are here, you prevent the software from accidentally breaking those good sections while it tries to resolve the rest of the project. It is essentially a way to tell the software, I've already fixed this part, so don't touch it, and just concentrate on the, let's say, broken scan. So now let's look at the result of 2 global registration options for this project, which contains about 3,000 frames. If you run a standard global registration on the entire project at keyframe ratio 0.6, you're looking at 660 seconds wait, about 11 minutes. And by using log frames on the scans that are already correct, you can isolate just the one troublesome scan. The algorithm now only has to calculate the registration for that single scan against the locked anchor of the rest of the project. As you can see on the slide, it reduces for this processing time to just 78 seconds. That is a massive speed profit, reducing your wait time by nearly 90% while ensuring the rest of your project stays exactly where it belongs. Our third and final use case for log frames is all about preserving accuracy in hybrid projects. When you combine data from different scanners, for example, using the high precision Spider 2 for the details and an EVA or Leo for the large geometry, you should first register your Spider scans perfectly on their own. Once you're satisfied, log those frames. This ensures that when you align them with the larger, slightly less precise scans, the high-resolution Spider data remains completely undistorted. This is also the standard workflow when using the Artec metrology kit or external targets. You log the scans that are already anchored to your high-accuracy photogrammetry skeleton. By doing this, you preserve that superior accuracy and force the neighboring scans to align to those fixed, reliable references rather than letting the whole project shift. In this example, we are looking at how to share accuracy between scans. On the left, we have Scan 1, which is our high accuracy foundation captured using targets and scan reference. And I've provided 2 views here, one in geometry mode and one with texture, so you can see the markers clearly. On the right is Scan 2. This scan covers a much more extensive area, but it was captured using standard geometry and texture tracking. Because it overlaps with our target tracked scan, we have a unique opportunity to improve its integrity. By locking the frames of Scan 1, we turn that high accuracy data into a fixed reference. When we run the registration, Scan 2 is forced to align itself to this perfect skeleton. This is a brilliant way to increase the accuracy of a large, complex scene by anchoring it to a smaller, more precise target-based scan. Now let's look at the numbers, because the results here are quite striking. As a reminder, our reference Scan 1 was captured with 0.05 millimeters accuracy using target tracking. If we look at the table, a regular global registration for our largest Scan 2 resulted in an error of 0.73 at a high keyframe ratio. However, by simply locking the frames of Scan 1 and using it as a high precision anchor, we were able to pull that error down to just 0.11. That is a massive increase in accuracy for the larger scan, essentially borrowing the precision of the target tracked data. This proves that you don't always need to scan an entire large object with targets to get high accuracy results. You just need to log a precise reference section. To conclude this section, let's go over a few advanced tips to keep in mind. First, remember that log frames is specifically designed for global registration. It won't stop other tools like outlier removal or the eraser from doing their job. Second, avoid locking scans that are feature poor. Oh, I said future, feature poor. These scans actually need global registration to improve their internal alignment. It is also important to remember that locked scans can still move as a single unit to find a better fit. The internal frames are frozen, but their global position is not. Finally, if you're using a small high accuracy scan as a reference for a much larger dataset, you must increase the keyframe ratio, KFR. This forces the software to treat that reference scan with the priority it deserves, ensuring it remains the anchor for the rest of your project. Okay, so now our second function, which is lock object, and you can easily distinguish it in your workspace by its icon. It's a classic padlock. While lock frames only affects global registration, the lock object status is far more comprehensive. It acts as a universal anchor. When an object is locked, it is shielded from any change in the workspace. This doesn't block movement during global registration. It also prevents any changes from the positioning, transformation, and even eraser tools. Essentially, if an object has that padlock next to it, its geometry and its place in the world are set in stone. Okay, let's just see again how it looks like in Artec Studio. As we discussed earlier, you can toggle this via the right-click context menu the same way. But the most efficient way is to use the dedicated lock column in your workspace panel. Again, a single click at this column for one scan, group of scans, or maybe the entire project. Everything is the same. Just remember to see the difference between two features. Okay, so as we look at the specific use cases for lock object, you'll notice they mirror the lock frames workflow in general. However, the key difference is that here we aren't just stabilizing the internal frames, we are anchoring the entire object in 3D space. So there are three main scenarios again, where this is a lifesaver, re-registering, preserving accuracy, and locking fusions. So let's take a closer look at these three examples to see where the unique power of the object lock really shines. Okay, for our first example, let's look at a common scenario involving a large industrial part, in this case, an engine component scanned with an Artec Spider. This project is relatively large, consisting of approximately 15,000 frames. So as you can see on this slide, despite our best efforts, some of the scans have registered fully, which would lead to errors in our final fusion if left uncorrected. As you can see, there are several, and you can imagine there are several ways to improve the result. Over the next few slides, we're going to compare these different solutions to see which one provides the best balance of speed and precision. The first one and most straightforward approach is option A, simply re-registering every scan, single scan in the project altogether. To try and fix the misalignments we saw on the previous slide, we increased the keyframe ratio to 0.6 for all 32 scans. Before the introduction of our lock tools, this was effectively the only way to resolve registration issues. However, the downside here is obvious time, because the software had to recalculate the position of all 15,000 frames from scratch. The process took over 20 minutes. In a professional workflow, that is a significant amount of downtime, especially if you have to repeat the process. Now let's look at our lock tools we can use to achieve the same or better results in a fraction of that time. Option B utilizes the lock frames tool to speed up the process. So first you locate all well-registered scans and set their status to lock frames. When you run global registration on the entire project simultaneously, this software treats those locked scans as fixed references. This targeted approach significantly improves efficiency, completing the task in just 11 minutes, nearly twice as fast as re-registering everything from scratch. But finally, we have option C, which is the most surgical and efficient approach, using the lock objects feature. Instead of involving the entire project, You just sort through your well-registered scans and identify only those that share a common area with your problematic data. You apply the lock object status strictly to these good neighbors, excluding the rest of the project. When you run global registration, the algorithm only calculates the relationship between your problematic frames and these immovable anchors. This strategy offers the ultimate speed profit, finishing the task in just 2.5 minutes. On the next slide, I will demonstrate once more exactly which scans to select for this process and which ones you should leave untouched. So let's imagine these are the most problematic scans, right? So to make option C as clear as possible, let's look at the selection map. First, we had identified these problematic scans, they shown here in red. These are the only ones that actually need recalculating. Next, select the good scans that directly overlap them, shown in blue. You must apply lock object to these blue scans, so they act as immovable anchors. And finally, the good scans in green should be left completely unselected. Because they don't overlap the problem area, they don't need to participate in the calculation at all. By focusing the algorithm strictly on the relationship between the red and blue zones, we achieve high precision results in that 2.5 minute time frame. Moving from industrial speed profits to accuracy preservation, let's look at our next application. In this second case, we focus on maintaining accuracy in projects that mix tracking methods. Here, scans 1 and 2 are our high precision anchors captured using targets. Now, a common mistake here is thinking that log frames alone will solve the problem. It won't, and here's why. If you only use log frames on scan 1 and scan 2, you are only freezing the internal data of those scans. However, during global registration, Artec Studio still treats them as two independent objects. This means the software could accidentally shift scan 1 a few millimeters away from scan 2 while trying to feed the new data from the scan tree. To preserve the high accuracy relationship established by your targets, you need to use lock object on both. This anchors them in the coordinate system and ensures that the distance between scan 1 and scan 2 remains exactly as the targets defined it. By locking the objects, you create an immovable, rigid accuracy block that scan 3 is forced to follow. And here is the result. You can see in the workspace that we applied lock object, indicated by the padlock icon, to our two high accuracy target scans. By doing this, we anchored their exact positions in the coordinate system. The result, as you can see from the uniform color, is a complete dataset where all scans are perfectly registered, and most importantly, the superior accuracy of our reference data has been absolutely preserved. For our final example, we are looking at how to use this tool in conjunction with positioning. As you can see in the demonstration, this is particularly useful when you need to place two objects in a very specific mathematical orientation, for example, at the perfect 90-degree angle. The workflow is straightforward here. First, you orient both objects together along a single axis. Then you apply the lock object status to one of them to fix it firmly in place. With that anchor set, you can then use the positioning tools to orient the second unlocked object along a perpendicular axis. Because the first part is locked, it won't move, allowing you to achieve exact relative positioning for complex assemblies where manual alignment isn't quite precise enough. So that brings us to the end of our first session in this series. We've covered how lock frames, stabilizes the internal integrity of your handheld scans, and how lock objects serves as a global anchor for your entire project. By mastering these two simple toggles, you can cut your processing times by over 90% and ensure that your high-precision data stays exactly where it belongs. Thank you for watching the webinar.